Okay, so for Unit 1 review, we're looking first at limits. So it's the limit of f of x as x approaches -4 from the left. So if you're coming from the left, moving right on the graph, your y's are going to infinity. -4 from the right, if you're coming from the right, approaching -4, so you're moving left on the graph. Coming from the right, your y's are approaching -2. Now we know at -4 it's undefined, but limit is asking what are the y's approaching. At -4, limit does not exist. Limit from the left, limit from the right are not equal. F of 4 also does not exist, or undefined, we could say. Limits, we say does not exist. F of, you could say does not exist or undefined. Limit of f of x as x approaches -2 from the left. So if you approach -2 coming from the left, so you're coming from the left, you're moving right on the graph, you are approaching, I'm sorry, -2. I was doing +2. So we're approaching -2 coming from the left, moving right. We're approaching a y value of 1, -2 from the right. So if I'm coming from the right, moving left, approaching an x value of -2, my y's are approaching 1. Or you can kind of think like from the right, it's like saying, well, what if I'm at -1.99999? Well, my y's are very close to 1. Same thing if you were doing from the left, you could say something to the left of -2, like -2.0001. Where's your y value? It's very close to 1, which means the limit of f of x as x approaches -2 is 1. Now, f of -2 does not exist, or it's undefined, because there's an open circle. There's a hole there. 1 from the left, so +1 coming from the left. So as you get closer and closer, to +1. So we'd be at -3. 1 from the right. So if I'm coming from the right, approaching an x value of +1. So if I'm at 1.0001, where are my y's approaching? 1, which means the limit at 1 does not exist. Limit from the left does not equal the limit from the right. F of 1 is 1, because that's where the closed circle is. Okay, next one is 2 from the left, so +2. So here we're at +2, coming from, I kind of made that slanted. For a +2, coming from the left, we're approaching a y value of 2. Coming from the right, we're also approaching a y value of 2, which means the limit of f of x as x approaches 2 is 2. Notice it's continuous there. So limit of f of x as x approaches 2 is 2. That means also f of 2 is 2. So if those conditions are true, then we know it's continuous. F of 2, there is no open circle. It is continuous there. Okay, so for limit, if I plug in, so first thing of limits is plug in. If I plug in, I get 0/0, which is the indeterminable form of limits, which means you need to do something else. So with radicals, we have to multiply by the conjugate of the, one with the radical. So limit as x approaches 1. Firsts, outers, inners are just going to cancel, and then lasts are going to give me minus x. Now on the bottom, I'm going to purposely, where I have the radical with the non-radical, I'm going to leave it factored. And we're going to see in a minute the reason I'm doing that. On the bottom, we have a difference of two perfect squares, 1 plus x, 1 minus x. And oops. And then we still have that 1 plus radical x. So these can cancel, and then I can plug in 1 plus 1. This is 1 plus square root of 1. That is 1 over 2. And again, 2, so 1/4. I just realized I was going to do these in separate videos, odds, evens, but I did number 1 and then I did number 2. So I think I'll just continue on now with odds. Now, this one, next one, if I plug in, right, because that's always the first thing to do with limits is plug in, I do not get 0 over 0 in determinable form. So that tells me I just plug in and I get my answer. Now, 5 is a limit as x approaches 4 from the right of that function. So just a reminder, if x was 4, we would have a vertical asymptote. So we're going to do a partitioning of the number line. So there's no hole in the graph. If there were a hole, we would just factor cancel, plug it in. Since it's a vertical asymptote, we have to know, is it going to infinity or negative infinity on whatever side of the asymptote we're trying to think about. Here we're doing 4 from the right. Here we're doing 4 from the right. Okay, so I'll just write over here, vertical asymptotes at x equal 4. So we are going to take the numerator, the denominator, and then we're going to pick something slightly to the left of 4, let's say 3.999. If I plug it in, this will be negative. This will be negative, which is overall a positive, so it'll be going off to positive infinity. If I pick something to the right, 4.001, that'll be negative, that'll be positive, which is overall a negative, meaning it's going to negative infinity. So from the right, 4 from the right, it's going to negative infinity. Okay, 7. This is looking like, if I plug in, I think I'm going to get 0 over 0 indeterminable form. So I'm going to do the limit as x approaches 3. I'm going to do a factor cancel, plug it in. Remember, you do not drop off the word limit until you're actually doing the limit, which is plugging in. So I factored, I've canceled. Now that I'm going to plug in, I can drop off limit. 6 over 9 or 2/3. 9, this is interesting to look at. If I plug in, I get 0 over 0 indeterminable form. So I'm going to actually rewrite this to the limit as x approaches 0. Sine x And if I think about it, let me go back up here and factor. If I factor out an x, so I can make sine x over x, and then I have a 1 over x minus 3. So if you think of multiplying those fractions through, you get what's up here. And then the limit as x approaches, so if I think about doing the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over x minus 3, this one is that rule where you have to know it's 1. This one I plug in, so it's 1 times negative 1/3, which is negative 1/3. Next one, plug in 3 cos 7 times 0 over 5, which is 3 cos 0 over 5. And cos of 0 is 1. So that's 3/5. So remember, sine of 0 is 0, tan of 0 is 0, but cos of 0 is 1. 13 is very similar to the number 2 that we did. You are going to multiply top and bottom by radical x plus 4, the conjugate. So it's the limit as x approaches 16. Wherever I have radical and non-radical, I'm going to leave it factored. Wherever I have the 2 radicals, I'm going to FOIL it. So first, give me x, outers, inners cancel out. Last, give me minus 16. And that's exactly why I wanted to leave it factored, because those will cancel, and then I can just plug in. Square root of 16 is 4. 4 plus 4, 8. 15, just plug it in, sine of pi. So sine of pi is 0. Either know that from your unit circle or your trig graph, your sine graph. Sine hits 0 at 0, pi, 2 pi. 17, plug it in, 2 times pi over 2 plus cos of pi over 2. This is pi. Cos of pi over 2 is 0, which is pi. And again, you can know that from your graph, or you could know it from your unit circle. At pi over 2, you're at 0, 1. Cos is the x-coordinate, sine is the y-coordinate. 19, limit of a constant is the constant. This is like saying if you had a y equals 24 line. So let's say this is y equals 24. I don't care where I approach, as I approach a value of 2 coming from the left or coming from the right, my y's are still at 24. 21, this is another practice of that radical t plus 2. So it'd be the limit as t approaches 4 of t minus 4, right? First, outers, inners cancel. Last, give me minus 4. Leave the radical with the non-radical factored so that those can cancel. So once you plug in, 1 over 2 plus 2, 1 over 4. Okay, now our limits at infinity. Remember, this is the work you have to show for limits at infinity. Limit as x approaches infinity. you are going to divide everything by x squared. And that's because that is the highest power of the denominator. So this is limit as x approaches infinity of, let's see, 4 minus 6 over x minus 11 over x squared, 7 minus 1 over x. Okay, so then we said as x approaches infinity, a constant over a really big number, that's going to go to 0, that's going to go to 0, that's going to go to 0. So it's going to be a constant divided by a really big number, which goes off to 0. So all that's left is 4 sevenths. 25. Oh, geez. Sorry. 25, again, you could think a constant over a really big number. That goes off to 0, right? If you were kind of to plug in infinity, even though you really can't plug in infinity. 27, this is the same as the limit as x approaches infinity. You can separate this, right? Of 1 minus the limit as x approaches infinity of 2 over x. Limit of a constant is the constant, so that's 1. This is 2 over a really big number, which goes off to 0. So my answer is 1. All right, this one, we're going to divide by x minus this one divide everything by x. So we get limit as x approaches infinity of 2 over 1 plus 1 over x minus limit as x approaches infinity of 1 plus 1 over x over 2. So that goes off to 0, that goes off to 0. We've got 2 minus a half, which is 1 1/2 or 3/2. 31, kind of just think of what 3x does as x goes to infinity. The y's shoot up to infinity too. Or you could think of plugging in a really big number that's going to get even bigger. 33. Given this, what should f of 3, or how should f of 3 be defined in order to make f continuous at 3? Well, f of 3 would have to equal the limit as x approaches 3 of 2x squared minus 5x minus 3 over x minus 3. That is our 3-part definition of continuity. In order to be continuous, the limit of the f of x as x approaches some value has to equal f of that value. So f of 3 has to equal the limit as x approaches 3. If I plug in, I'm going to get 0 over 0 in determinable form. So I'm going to do a factor, cancel, plug it in. So we're going to want 1 here, 3 here. Outers, that would be 6x. So minus 6x plus 1x will give us a minus 5. Those cancel. So now f of 3, I can plug in. It'd be 2 times 3 plus 1 over, that canceled to 1 over 1. So basically, f of 3 equals 7. "35, state the 3-step definition of continuity, and then find the value of k that makes f continuous on the entire real line." Okay, so continuous basically everywhere. Now for the 3-step definition, one way you can just say it in one sentence is you could say f of x is continuous at x equals a if the limit of f of x as x approaches a equals f of a. Sometimes people say x equals c, then as x approaches c equals f of c. It doesn't matter. You could use k, you could use whatever letter, but I'm using a there. Or you could say it in the 3 steps. You could say f of a exists, the limit of f of x as x approaches a exists, and 3, basically they're equal. Limit of f of x as x approaches a equals f of a. So you can literally say it in the 3 steps if you want to. So that's an either or. Okay, so then in order for this piecewise function to be continuous, the limit of f of x as x approaches 6 from the left would have to equal the limit of f of x as x approaches 6 from the right, right? That's so that the limit would exist. So let's see. From the left, this is the region from the left. So I would plug in, say, 6 squared plus k. From the right, I'd be using this top one, 3 times 6 minus 7. 36 plus k. 18 minus 7 is 11. Minus 36. K is negative 25. And we know f of 6 exists, right? Right, because f of 6 would be then 6 squared plus the k, which is negative 25. 36 plus negative 25, which is 11. All right, 37. Okay, does the function cross the x-axis between 0 and 1? Explain your answer using concepts of calculus. This is our IVT. So we got to do f of 0. We got to do f of 1. Okay, so this is less than 0. This is greater than 0. So we have a sign change in here. So basically, if the y is going from negative to positive, if the function is continuous, so yes, we know f of x is continuous. because it's a polynomial function. So remember, any polynomial function is continuous. Therefore, by IVT, f of x has a 0 between x equals 0 and x equals 1. And that's because we've said, one of them's less than 0, the other's greater than 0. So if it, somewhere you're hitting 0 in the middle of that, if the function is continuous, which it is because it's a polynomial function. All right, so that's it for the odds.